If you want to write really effective, high-performance Go, you absolutely have to get your head around slices. Now, they seem pretty simple on the surface, right? But there's this powerful secret hiding just underneath, and today, we are going to pull back the curtain and uncover it. Okay, let's just dive right in. To really get why slices are so brilliant, you first got to look at the problem they were built to solve. Arrays in Go, well, they're rigid. You pick a size, and that's it, you're stuck with it. They can be a real pain to pass around. And that's where slices come in. They are the solution. They're flexible, they feel dynamic, and they are just incredibly powerful. So what is a slice, really? This is it. This is the core aha moment for pretty much every Go developer. The key thing to realize is that a slice doesn't actually hold any data itself. Nope, it's way more clever than that. Think of it like a window. At its heart, a slice is just this tiny, super lightweight structure. It doesn't store the actual items. Instead, all it does is describe a piece, a slice, of a bigger array that's living somewhere else in memory. It's literally just a view into that data. This little three-part structure, this is the entire secret to why slicers are so awesome. It's made up of a pointer, which points to the actual data, a length, which tells us how many things we're looking at right now, and a capacity, which tells us how much room we have to grow. These three little fields are what make the whole thing so fast and so flexible. And that leads to probably the most important thing you need to understand about a slice's design. When you copy a slice, you're not copying all the data. You're just copying that tiny three-part header. This is why you can have lots of different slices all pointing to and even changing the exact same underlying data. And for performance, oh, this is a total game changer. Passing a huge slice with, say, 1,000,000 elements to a function is incredibly cheap. Why? Because you're only copying that tiny little header structure. And because the pointer inside still points to the original array, any changes that function makes to the data, yep, the original caller sees them immediately. So we know slices are flexible, but what happens when you need to add more data than you originally planned for? How do they actually grow? This is where understanding the difference between length and capacity becomes absolutely crucial. It is so important to keep these two ideas separate in your head. The len function gives you the current length, how many elements you're actually using. But the cap function, that tells you how much room you have to grow within the current backing array before things get a little more interesting. And that is the million-dollar question, right? You're happily appending items, your length is going up, 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 and suddenly you need your link to be bigger than your capacity. What on earth does Go do then? Well, the built-in append function is super smart. First, it checks if there is enough capacity. If there is, great. It just adds the data, bumps up the length. But if not, this really fascinating thing happens behind the scenes. Go allocates a completely new, bigger array, copies all of your old data over, adds the new stuff, and then, and this is key, it gives you back a brand new slice header that points to this new array. And that's the reason you always have to assign the result of append back to your slice variable. You'll see it all the time. My slice equals append my slice new item. You have to do it, because if a reallocation happened, append just handed you back a new slice header. If you don't save it, your variable will still be pointing to the old, smaller, now out-of-date array. Okay, awesome. We have got the fundamentals down cold. So now let's take this knowledge and apply it to something you'll definitely run into, building a 2D grid, like for a game board or an image. How does this whole hidden array thing work when you go to 2 dimensions? So here's a fun little quirk of Go. It doesn't technically have 2D slices. What you actually do is create a slice of slices. Just think about that for a second. It's a slice where each element is itself another slice. This is actually super powerful because it means every single row in your grid could have a totally different length if you wanted it to. This brings us to a really interesting strategic choice. When you go to build that grid, you have 2 main ways you can set up the memory, and the path you choose has real-world consequences for your application's speed and performance. So here's the trade-off. On the one hand, you can create each row one by one, independently. This gives you a ton of flexibility, but it also means lots of separate memory allocations, which can be slower. Or you can do this really cool optimization. You allocate one single giant backing array for the whole grid, and then you just create little slice headers to act as views into each row. This one-shot allocation is way faster, but it does lock you into a fixed grid. The choice really comes down to, do you need performance or do you need flexibility? Whew, okay.
we have covered a lot of ground here, right? From the basic anatomy of a slice all the way to these advanced allocation strategies. So let's bring it all home and just recap the key things you need to remember.
Let's just lock these 5 ideas in. Number 1, a slice is just a header, a view into some array. 2, always distinguish between its length and its capacity. 3, and this is critical, always reassign the result of append in case a new array was made. And finally, be smart and strategic when you're allocating 2D data. Mastering these concepts is really the line between writing Go code that just works and writing Go code that is truly efficient and professional. So, the final question is for you. This isn't just theory, right? Understanding that hidden array, it changes everything. It impacts performance, memory, and it can help you avoid some really nasty, subtle bugs. So now that you can see it, now that you know it's there, how are you going to build your Go programs differently? Thanks for tuning in.